Welcome everybody. Welcome everybody to this webinar on automotive technology, building the EV of the future. This is a joint seminar between HIOKI and ETAS, and I want to welcome you all for that. So before we get started, I'd like to start with a quick poll question. Okay, and I don't see the poll right now. Let me see if I can get this started. Okay, here we go. So the poll question here to get us all warmed up is what industry are you coming from? I'd be curious to understand who you all are, what drives us to us, what makes you listen to this webinar. If a few choices, there's automotive, there's industrial, solar, and of course, other industries. And the second question is, what's your primary job title? Is that electronic hardware design and development and testing? Is that more related to control systems and controls engineering, software verification and software validation and testing? Is it final calibration? Or is it possibly another job description that's not in this list of choices? Let me give it a few more seconds. Okay, I think it's stabilizing there. Thank you very much. Let's stop the poll here and see. So most of you are coming from the automotive industry, which makes sense because this webinar is about automotive testing and EVs. And the primary job function is very well spread out. Most of you are somewhere in the other category. So thank you very much for participating. Really appreciate that. Before we begin, let me give a quick introduction about our company. So I mentioned it's a joint webinar between HIOKI and ETAS. HIOKI was established in 1935. That is 4 years before HP was founded, by the way. We have been growing to become the world leader, providing consistent delivery of test and measurement instruments through advanced design, manufacturing, and sales and services. We provide over 200 main products that are characterized by safety and quality while meeting an expansive range of application. We aim to contribute to the efficiency and value of our customers' work in research and development, production, and electrical maintenance. Our products and services are available around the world through our extensive network of subsidiaries and distributors. For more information, please visit our website at HIOKIUSA.com. A few words about ETAS. ETAS is a single source of reliable, cutting-edge software and hardware tools and services that make embedded systems safe and secure for the transportation industry. Built upon in-house resources and unique expertise, ETAS' multifaceted portfolio includes tools and services for every stage of the development cycle. Expertise in automotive cybersecurity lies within the E-REV brand. Together, ETAS and eScript provide peace of mind to its global customer base throughout consulting, engineering, design, integration, and testing. Established in 1994, ETAS is a 100% subsidiary of the Bosch Group, with international locations and sales offices in Europe, North and South America, and in Asia. You can get more information by going to ETAS website at etas.com. One more thing before we get started. So what you're going to see in this webinar is a presentation from HIOKI and ETAS. There will be a moderated question and answer session at the end of the presentation. There will be a demonstration before the question and answer session. So we will not stop to answer questions during the presentation, but please feel free to ask your questions by clicking on the Q&A box in the bottom of the screen. We have a team of panelists to stand by that will answer the questions directly, and we will also answer the question at the end of the presentation. The session will be recorded and will be available online after the webinar. With this, I'd like to introduce our speakers. Let me start with myself. I'm Chris Schultz. I will be moderating the session. I am product manager at HIOKI USA. I have 17 years experience in the test and measurement industry. Previously, I was a product manager for vector network analyzers with Roland Schwartz, North America. I do have a few advanced degrees, the latest from Georgia Institute of Technology in electrical engineering. Next, we have Enrique Mongino. Enrique is a field applications engineer for measurement and calibration at ETAS. He joined ETAS in 2010 and has been working with applications for automatic drive and active safety, performance vehicles, hybrid electric, off-highway and classic powertrains. Enrique holds an engineering degree in mechanical engineering from the Polytech School of the University of Sao Paulo and an MBA from the University of Sao Paulo. Next, we have Kevin Lee. Kevin Lee is an application engineer. Before joining HIOKI, he was a suspension system product development engineer at Karma Automotive. He spent there 5 years. He holds a bachelor's degree of science in applied physics from the University of California at Irvine. Then we have our panelists. Our first panelist is Tim Foster. He currently manages the measurement and calibration solution business of ETAS. He has had various technical sales and product management positions in his more than 20 years at ETAS and has more than 30 years experience in the area of automotive powertrain electronics development. Tim Foster holds a bachelor's degree of electrical engineering from the University of Michigan in Ann Arbor. And last but not least, we have Naomichi Miyari. He began his career as an electrical engineer, and he's currently working as product manager at HIOKI USA and has been with HIOKI for more than 10 years. He holds a bachelor's degree of chemistry and a master's degree in chemical engineering from the Yokohama University in Japan. With this, I want to again thank you all for attending this webinar and pass the ball to Kevin, who will give you an introduction on the automotive testing. Kevin.
Thank you, Chris. Thanks for the introduction. And thank you everyone for attending our webinar today. So today we'll be going over a few topics, industry trends of inverters, along with all of this new technology, the importance of precise measurements. We'll also be going over some challenges we face in power measurements. After that, we'll give you a brief overview of our HIOKI hardware, so the 3390, the PW6001, and the lineup of our current sensors. After that, we'll be passing the ball over to the ETAS team, and we'll close this out with a live demo, and then after that, the Q&A session. So let's get started. So first, let's talk about inverters. So we have basically three types of inverters, each with their own operating frequency and current, as you can see from this graph. In the highest power applications, we have a bit of overlap between the silicon and silicon carbide and silicon. We also have the gallium nitride. Typically, that one operates at a higher frequency than the other two. So now between the silicon and silicon carbide, the silicon carbide offers us better overall performance, efficiency, and again, operates at high frequencies. This has the benefit of being, this one has the benefit of being more compact than the silicon ones. There's also a reduction in the switching losses as well. We can see from the usage that these are typically used in automotive, train, or even airplane applications. Again, now there's alternatives to using silicon, such as gallium nitride. Now these offer high power density, also have lower power requirements, and can help lead to better efficiencies as well. Gallium nitrides have been proven to be very reliable, efficient, and effective. So these are typically in your smaller devices, such as PCs, your PCs or your smartphones. So overall, though, all of these inverters can operate at fairly high frequencies, which will cause us to have some trouble taking measurements in terms of precision and accuracy. And we'll go over why we have those issues in a bit. So when we want to accurately measure our inverters, we need to know the components of the inverter output. So the inverter output includes the fundamental frequency, the harmonic components, the switching frequency, and its harmonic components. Of these, the fundamental is the dominant, the fundamental wave, its frequencies, its harmonics, the switching frequency, and its harmonic components can be observed. But remember, the current falls kind of abruptly as our frequencies increase. So this is because our impedance grows at higher frequencies. This makes it harder for the current to flow. So in order for us to take good measurements, we also need to have good sensors that are capable of measuring active power, not only for the high power factor fundamental wave and its frequencies, but also the low power factor for the switching frequencies and its harmonic components. So we have a graph here that shows the relationship between our phase angle or our phase error and the active power error at different power factors. You can see here that the voltage and the current phase error in the measurement is greater on the active power at low power factors than at the higher power factors. So in order for us to take accurate measurements of the active power at the switching frequencies and its harmonic components, we need to have testers that have both a flat amplitude and flat phase characteristics. And that needs to be across a broad frequency band. So it's also important that not only our meters have these characteristics, but our current sensors as well. So when we're doing all these measurements, it's also important to have all of the measurements synchronized together or using one device to take all the measurements simultaneously. This will allow us to calculate all the efficiencies and losses with better precision. Also, when we're taking these measurements, it's important that we position the conductors at the center of our sensors, since all current sensors are susceptible to the effects of the position. So keep in mind, the sensor's measurement accuracy is always defined at the center position of the sensor. So when we're measuring at these high frequencies, it's important for us to keep those in the center for high precision and more reproducible measurements. And because these current sensors work by detecting the magnetic field produced when the current flows through our cables, we need to make sure that we keep any conductors away from the sensors if possible, since the effects will be more significant at the higher frequency currents. So we were talking about the higher frequencies introducing a greater phase error. So current sensors typically will exhibit this gradually increasing phase error in the higher frequency region, simply because of the characteristics of the sensor's magnetic core and the circuitry. Also, different sensors will have different amounts of error. So the through type that will eliminate any breaks in your magnetic core, which makes it easier to obtain like uniform characteristics around the entire circumference of your core. And this allows for extremely precise sensors. This design, though, kind of makes it difficult to disconnect your cables. On the other hand, we also have like the clamp types, which has a break in its magnetic core, but this allows us to conveniently clamp onto wires we wish to measure. But because there's the break in that core, this makes it a little bit more difficult to obtain that uniform characteristic. So the clamp type sensors will generally have less accuracy, and those will have a greater effect on the position of the wire than the through type sensors. So as we know too, with these new inverters, they produce a lot of noise. So this will make it difficult for us to take good measurements. So since a power analyzer will measure your line voltage, a large common mode voltage is applied across all of the channels. So this common mode voltage includes the switching frequency and the associated harmonic components. So for us to do this, the power analyzer needs to have a high common mode rejection ratio for the higher frequencies. So because the frequency of the switching frequency increases, so does your common mode voltage. And again, because the newer inverters are designed with increasingly high switching frequencies, it's really important we choose a power analyzer with high common mode voltage rejection. So when we're measuring the inverters with the high capacity, we need to measure the large currents on the order of several hundred amps. So to counter the effects of the noise from the inverters, so we can get accurate power measurements. So you can do this by connecting the power analyzer and the current sensors directly together. So we have a graph here that shows the relationship between the sampling frequency and analog band in a typical power analyzer. So we see that in similar instruments that the voltage and current components exist in frequencies higher than the sampling frequency. This will appear in the low frequency domain as folding noise, or also known as aliasing. So when measuring our measurement targets, these include the frequency of components across a broad band. And sometimes it becomes impossible for us to distinguish between the folding noise and the actual noise. So all of this kind of means that we have additional measurement errors and reduced repeatability. So it's more likely for us to detect false harmonic components. So when measuring and analyzing our inverters, it's necessary for us to be using an instrument that has a high sampling frequency, and it's capable of simultaneous broad power measurements, accurate harmonic analysis, and also accurate FFT analysis. So now I just want to jump into giving you guys a brief introduction to our power analyzers, the PW6001 and the PW3390. So let's talk first about the PW6001. So this offers us a really good world-class accuracy of 0.02% with improved DC accuracy and sensor combined accuracy. So DC accuracy is a key consideration when we're measuring energy conversion efficiency of like DC AC inverters, which are used in EVs. We also have an 18-bit converter, which converts the analog signals to digital signals. This will result in increases in resolution that make precise measurements possible. It also has a broad range of measurement frequencies. This will allow us to measure inverters with high switching speeds, and this is actually 10 times wider than that of the 3390. We can also use this to perform waveform analysis, which is necessary when we are measuring energy conversion efficiencies. We're also able to measure up to 12 channels when we combine two of the 6001s together. And if we want to properly measure energy conversion efficiency with like high levels of stability, it's also important that we reduce the effects of the noise. So luckily with the 6001, it has an increased noise resistance, and this is thanks to some of its solid shielding. So now let's jump over to the 3390. Now this has a basic accuracy of 0.04. This meter is able to also deliver precise measurements as well, but the measurement band is only at 200 kilohertz for its measurement band. It's also able to capture waveforms with 500 kilosamples per second for its sampling speed, and it can perform 5 calculations in real time. Another benefit with the 3390 is that you can connect multiple units together and synchronize up to 8 units. So this will give you 32 channels in total. Now, both of our testers will feature a flat response characteristic, and they both have the built-in phase shift function. And we'll get into this in a bit, but this allows us to set and correct the phase error of our current sensors. And this will dramatically reduce the measurement error when we're measuring the high frequency, low power factor power. So let's also talk about our current sensors. So current sensors in general utilize a broad range of detection methods. At HIOKI, we use the zero flux method in order to provide high precision and a wide band. This method has the advantage of minimizing the effects of magnetic material nonlinearity, since the operating magnetic flux can be controlled so that can be kept to a very low level. Our sensors combine the flux gate method as well as the current transformer method. The flux gate method allows the detection of based on DC current and doesn't require any use of semiconductors, giving us the advantage of temperature stability and a low offset voltage. So we are also able to offer sensors with a 0.02% accuracy and a band of 3.5 megahertz. Our sensors are also able to operate between negative 40 degrees C all the way up to 85 degrees C. There's a few key considerations when we're choosing our current sensors. So there's a lot of high precision current sensors that use the current output method, but our HIOKI sensors will use the voltage output method. So the current method is regarded for its signal transmission quality, but the voltage output provides us with a few advantages. And we'll get into that right now. So what we need to keep in mind is the rated current and the frequency band. For us to measure the current with a high degree of precision, that requires us to have a sensor that is rated for the magnitude of the current target. And also all of the sensors that we have at HIOKI are rated as RMS values, while many of the other ones are rated using peak values. It's also important for us to verify that all the frequency components of the current can be measured are included in that bandwidth. So most high precision current sensors are only defined for DC current and commercial frequencies, and the phase accuracy is rarely defined. So since our sensors are voltage output, it's possible for us to define the entire measurement band. So versatility is also important. Current sensors that use the voltage output have the ability to be used in other applications, since it's easy to plug them into other instruments such as like multimeters, oscilloscopes, or even recorders. When choosing a current sensor, you should also be aware that you should have a high signal to noise ratio. And they should also be easy to adjust and calibrate. And typically the voltage output sensors are easier to adjust and calibrate. So before we were talking about needing a flat response and the phase error as we get to the higher frequency ranges. So we have a phase shift function that allows us to correct for that error. So our phase shift function utilizes virtual oversampling to perform real-time deskewing for the sampled waveforms at a high time resolution, and that's equivalent to a frequency that is 400 times higher than the actual sampling frequency. Also, by performing delays in compensation for the waveforms, the phase shift can be extended across the full frequency band. In addition, so we've been able to characterize our high precision current sensors so that each sensor has a specific phase characteristic that can be inputted into the power analyzer for this phase correction. Another thing I would like to go over is the efficiency calculations. So when we're measuring, for example, DC-AC converter efficiencies, accuracy is required not only for AC, but also for DC. So the accuracy of both the PW6001 and the 3390 allows us to make accurate and stable efficiency measurements. You're also able to set up equations on the power analyzers to compute measurement values however you want and get your results in real time as well. In particular, we were able to simultaneously measure inverter input and output and the motor output. So what does this do? This helps us evaluate the overall system efficiency and loss in an accurate and reproducible manner. We should also keep in mind for us to improve the accuracy of our calculations, again, that all the measurements should be taken simultaneously, because if we don't synchronize everything perfectly, this will affect our results. Also, if you want to create like a efficiency or loss map, you can take the measurement results from the power analyzers and you can plot them onto MATLAB. So we have our first quick live poll that we have for you guys, with the question being, what features of the HIOKI solutions would best help your development? So we have the wide bandwidth, the noise resistance, the phase shift function, or just simply the accuracy of the meters. It looks like some of you are starting to fill in this poll, so thank you everyone who's completed it so far. Looks like most people, maybe a little bit neck and neck between noise resistance and the accuracy. Almost half of you guys have voted. We'll give you a little bit more time to vote here. It's pretty interesting seeing that it's the accuracy. Let's see if we get at least half, almost there, almost there. All right, thank you everyone for voting. We're gonna close this out now. And it looks like the most important, or what feature would best help you guys, is the accuracy. So thank you everyone for doing the poll. So now I would like to jump over and pass the ball to Enrique.
Okay, thank you, Kevin. Thank you. I'll first start talking about ETAS and our solutions for automotive embedded systems, giving a special focus on measurement and calibration applications. And after that, I'll show a live demonstration on the integration between HIOKI and the INCA system with ETAS measurement and calibration software. So we all know that embedded software plays a key role in modern vehicles. It ensures they are clean, economical, while improving safety, comfort, and driving characteristics. And ETAS has been offering for over 25 years solutions to develop, operate, and secure automotive embedded systems and software. We offer products, consulting, and engineering services in all the embedded software development domains, starting with software engineering, for the implementation of the actual base and application layers, and going through test and validation with HIO, SIL, and MIL solutions, hardware in the loop, software in the loop, and model in the loop solutions, and also measurement and calibration, real-time applications, and cybersecurity. The focus of today's webinar is measurement and calibration, and that is basically the refinement of the software by changing calibration parameters based on the measurements of the controller, internal parameters, and of external sensors. In this area, ETAS offers a robust solution that consists in a core software called INCA, and hardware interfaces for ECU access and also for measurement of physical parameters. To understand more what INCA does, we need to review what is measurement and calibration and what are the basic tasks of a calibration engineer. Calibration in automotive world is an interactive task where you can change a calibration parameter, you can measure how your system responds to such change, and then you analyze the response. And this is a cyclic process that demands a tool that is capable of enable simultaneously change, measuring, and analysis. And this tool is INCA. These calibration tasks, they are usually performed to refine the vehicle application software and also to enable it to achieve specific targets, such as emission regulations, OBD and diagnostic requirements, engine injection and ignition management, or even calibrate the vehicle to perform in extreme weather conditions like a cold start. And in such contexts, monitoring real-world data from the physical sensors in parallel with ECU data is essential. And INCA is the tool that we have that ETAS has for such tasks. And it's being used by almost all the manufacturers, OEMs and tier ones. And it supports methods, process for several applications, such as in-vehicle, test bench, dyno cell measurements, and calibration. It's also used in many application fields like powertrain, chassis controls, and even in modern drive assistance or autonomous driving development. As an example, we can use a hybrid electric application here. So in such scenario, INCA will be the platform, and let me just use a pointer here. INCA will be the platform that controllers, several additional models for mirror roof, seat, brake control, inverter, camera, and brake. And all that is connected to the automotive buses here, as an example, CAN-FD and automotive Ethernet. And INCA is the platform that integrates all that data from the ECU via CAN, automotive Ethernet, or direct access to the micro, with the data from the sensors and also for special measurement instruments like the power analyzer from HIOKI. And all these measurements, they are now seen in INCA into single experiment interfaces and recorded at a synchronized time basis. So in parallel, the measurements of the variables, INCA can also access the ECU calibration parameters, and that allows you to calibrate your vehicle in real time while monitoring the immediate response of the system to the applied changes. So you measure the data from the controllers, from the sensors, you do your calibrations with INCA. INCA changes the parameters in the ECU, and you receive in the same platform the feedback from your calibration. That's the whole idea here. And for the integration with the HIOKI Power Analyzer, we have recently developed an add-on, INCA add-on that supports the Power Analyzer PW6001 and PW3390 that Kevin mentioned before. And the add-on, it brings data from the Power Analyzer into INCA experiment in cycles of 10 milliseconds. This way, calibration can be performed, having measurements from the Power Analyzer in parallel with CU data and also from the other sensors. Efficiency loss and all the additional data from the Power Analyzer can be used as an input to INCA, and INCA can calculate signals with that or manage recording triggers. And all this data is synchronized and recorded in a standardized automotive file format, the ASM MGF. For the demonstration here, that we have a live set today, I will first explain the hardware set that I have on the table using the diagram here. Then I can go to a live demonstration in INCA experiment environment. And at the end, I can show the actual hardware and its connections. So the target system consists here in an ECU with inverter, battery, motor, and load. The HIOKI Power Analyzer here, we are using the 6001. Is measuring voltage and current between battery and inverter and on the all three phases of the motor, and also using as analog input the torque and rotation here from the motor. The Power Analyzer is connected to the ETAS box. This is ETAS ES886 using an Ethernet cable. So there's an Ethernet cable between the Power Analyzer and the ETAS box. And this ETAS box, the ES886, is the ECU interface that we have that supports CAN, CAN-FD, and also automotive Ethernet. The 886 is connected to the ECU using a ETK connection that is a ETAS proprietary format that has specific access to the micro and also to the CAN data bus. From the ETAS box here, the 886 to your computer, we have another Ethernet cable, and then in the single platform here that is INCA, it's possible to see and record the data from the ECU and also from the HIOKI power analyzer in a synchronized time basis. So what I will demonstrate will be the INCA experiment platform. And then after that, I'll turn on the camera that is connected to the hardware set, and I can do a walkthrough on the hardware connections. Now we have a quick poll while I turn on the camera. I'll ask Kevin to please read the questions, and then I can transition to the demonstration, to the actual demonstration.
Yep. So for this poll that we have here, what kind of vehicle data is relevant to your application? So here you can choose more than one, fun fact. So the first one we have is CAN or CAN-FD. The next, automotive Ethernet, LIN, calibration protocols, or physical sensor data. Quite a big mix of things, but it looks like you guys are most interested in CAN or CAN-FD, or even physical sensor data. Almost about half of you guys have voted here. So we'll give you a little bit more time, maybe 15 more seconds before we close this out. Yeah, it looks like most important is CAN or CAN-FD. So we'll probably close the poll here now, a little bit more than half. Majority of you guys voted for CAN. So thank you everyone for the quick poll, and I'll hand it back to Enrique.
Okay. So here what you can see in your screen, it's INCA experiment environment. And from here, we can trigger the access to whatever is connected to the INCA laptop. So in the variable dialog here, variable selection, I can see all sources of data that I have in my system. And as I described before, I have an ECU access, a CAN node, and I have the HIOKI power analyzer. I have prepared an experiment here that from HIOKI power analyzer, I'm getting the efficiencies, losses, all the power measurements, and also speed and torque that is being collected over the analog input. And from my ECU here, I have a few parameters and also a calibration map. Here from INCA experiment environment, you can start measuring, and you're gonna now see data flowing in live demonstration here. So we have in this first black box here on your top left is the speed of the motor that we are reading by CAN over ECU. So this is the CAN channel. And then all the windows here that are labeled PW6001, they are actually being measured from the HIOKI system. And all that integrated into the same platform. For my ECU measurements, I can bring additional windows here with all the display data, and I can also do calibration maps. So for calibration here, I can do calibration in real time, select a region of my map, and change the calibration base map, and all that in real time while I'm measuring the data from the HIOKI system here. And to simplify the demonstration here, I put the measurement values into a diagram that will show exactly the point of connection that they are. So the power drive system here, efficiency and loss, the battery output, voltages and power, the three phases of the motor here, efficiency and loss on the inverter, and efficiency and loss at this point as well, and also the access of the CAN bus. So this diagram here shows the connections here where I'm bringing up the data. And Inca will also be able to record that. So if I start recording, I'll create a file, and this recorder has several possibilities and flexibility that you can do. Like you can record based on a specific variable. Like let's say I'm just interested when efficiency or loss goes through a certain threshold, and then I need to record data for 2 minutes or something like that. So Inca has the capability and flexibility to configure the recorders the way that is more convenient for you. And once you stop recording, all the data from the ECU, from the CAN channels, from the additional sensors, it's saved into a standardized automotive format that is MDF. Okay, so let me now go to the hardware set. So let me see here. This is the kit. This is the kit that we have a motor, inverter, and battery, and we have the current sensors from HIOKI on the points that I mentioned before in the diagram, and also we are collecting the voltage of each one of these points, and this goes to the power analyzer. So the power analyzer, all the probes, the sensor current probes are connected to the power analyzer, as well as the voltage levels and the analog signals for torque and phase of the motor. From the HIOKI system here, we have an Ethernet cable going to the ES886. The 886 here, again, it's our box that has ECU interface for automotive Ethernet to CAN channel. So this is the cable that is connected to the HIOKI system. And this is the cable that is connected to the ECU over CAN. So this is my CAN cable. And the last cable that you are seeing here is the Ethernet cable that is going all the way from the box to my PC. So you can see the live data in Inca. And that's the demo set here that I have on the table. Okay, so I'll now transition back to Kevin. He has a summary and a wrap up. Thank you.
All right, thank you, Anike. Thanks for that portion. I believe everyone can see my screen now, but so thank you, everyone. So let's wrap up before we move over to our Q&A section. So we spoke about how next generation inverters today operate at the higher frequencies. We then spoke about how because of these higher switching frequencies, this will cause us problems such as phase error. We spoke about the need for high common mode noise rejection, and then touched upon our HIOKI solutions and how they can assist you with taking precise and accurate measurements. We touched on our phase shift function that can help account for that phase error, helping you take more accurate measurements in real time. Finally, we discussed our collaboration with ETAS and how this pairing can help streamline your calibrations, and gave a demonstration of the system. So with that, if you guys want to reach out to us, here's our contact information. HIOKI, we're out in Plano, Texas. And if you want to reach out to the ETAS team, they're out in Ann Arbor. Contact information should be on your screen as well. And with that, I'd like to now open up the floor for our Q&A.
And Kevin, thank you very much. And Ricky, thank you very much. Thanks for the demo. And thank you all in the audience for your questions. I know now and Tim have been busy answering questions already. Let me take the question and answer session is still open. So if you want to have any questions answered, please use the Q&A box in the bottom of the screen. Ask your question, we will answer them as they come in. I have a few questions that came in already. Let me get through the list here. There's one question, will we discuss range testing and emission testing in this presentation? No, we don't, but we are very engaged in that. I mean, the question is related to if your EV has 100 miles per gallon, how is this measured? There's no gasoline being burned, so And of course, how do you get an equivalent emission standard? Standards are involving, so we are very involved in that, both ETAS and HIOKI. Ping us directly, we'd love to discuss that thing. That's just a little bit off the topic that we want to discuss in this webinar, but yeah, it's a very important topic. The next question I have, that's a question to now. You measure current by connecting the meter to the device directly, for the power analyzer to the device directly. What is the major advantage of using current sensors over direct connection method?
Yes. So the direct connection method. So I see several advantages over the direct connection method. So the direct connection method usually needs long wires to put a meter in between devices, such as motor and the inverter. So the meter is put in between a motor and the inverter to measure current. So in that case, we need to use long wires. So long wires lose more energy in there. And long wires create stray capacitor, more stray capacitors. Then it increases leakage currents. So, but the current sensor method can eliminate those negative effects. It can contribute to more accurate measurement. Thank you.
Thanks now. Let's see, the next question I have, I think that's a question for Tim. Tim, question here, somewhat interesting in the demo that we have. Can I easily modify the INCA experiment to include additional buses and or sensor data?
There we go. Sorry about that. Yeah, that's INCA is very expandable and let's say modular. So you can easily add in additional analog measurement devices, additional measurement buses. I saw in the poll there was several people interested in CAN, CAN-FD, automotive Ethernet. We support our ECU high bandwidth interfaces, what we call ETKs as well, and you can easily configure the setup to your needs and even move from test cell to test cell or vehicle to vehicle, depending on what your setups are. And you can also take those configurations and you can export them and provide them to other users in your group who are doing similar testing or slightly different testing, and they can easily modify those experiments as required.
Thank you, Tim.
Yeah.
And there's another one for you, Tim. Here's same thing to the related to setup. Once the INCA and HIOKI experiment is created and working with one specific motor, so if it's created and working with one specific motor and inverter test, how easy is it to move this test set to another test system?
Yeah, so I think I kind of inadvertently answered that question as well in the previous time, but the INCA's got a function that allows you to export those experiment configurations to be able to send them via email or just USB stick into other colleagues, so they can easily take those and use them in other setups or modify them as required.
Perfect. Thank you.
I also see another question that came in here, probably that I should take as well, regarding MDA, what we call MDA, Measure Data Analyzer. And so the question, I'll just go ahead and read it if that's okay, Chris.
Absolutely.
All right, so the question came in, do you use Measure Data Analyzer version 8 to analyze your measurement? And yes, that's one possibility. This is what we would recommend, obviously, because that's one of our products, and it obviously fits nicely within the setup. But you can also export your data to other formats if you have a preferred data analysis package. That you could export it to a .m format, for instance, or a CSV format. So So Inca easily allows you to export the data into various formats as well, or to use our measured data analyzer package that comes together with Inca.
Perfect, thank you. I hope this answers the question. If you have further questions, let us know. We still have the question and answer session open. Here are two more questions on harmonics and inverters, and I think that's mostly for now. But Tim, please feel free to chime in if there's anything to add. What order of harmonics should be considered for an accurate power measurement?
Yeah, so in the automotive applications, we usually measure motor power or inverter power. And usually a motor is connected in the drivetrain, so which is considered as an inductive element. So voltage signals can be seen a broad range of frequency in the measurement, but regarding current harmonics usually suppressed by inductive components like motors. So you said that up to 5th or 7th order of harmonics of the carrier frequency or switching frequency is required to be measured accurately for accurate power measurement. So 5th or 7th is my order of harmonics. That's my answer.
Oh, thank you. And the next question, kind of related, do designers of modern inverters have a lot of difficulty meeting EMC standards?
Yes, I think that is my question. And yes, so modern inverters, we can see silicon carbide inverter and gallium nitride inverters. So carrier frequency or switching frequency is getting higher and higher. So that means noise can increase more and more. So to meet standards, EMC standards, we need to suppress such noise from the inverters. So yeah, it's difficult, but recently many noise suppression devices are emerging. So yeah, it's kind of difficult to meet EMC, but we now have some solutions out here. Thank you.
Thank you, Now. And so here's one more question that just came in. Now, I'm not sure who should I send that to. That's Now or Tim or maybe both. So the question is about synchronizing data, and he's saying that most data in automotive industry as reference to angle of or rotation can be synchronized data to a PLL.
So to do power measurement in the power analyzers, PW6001 or PW3390, you can choose a voltage source and current source as a synchronization source. But also you can use phase for motors as a synchronization source. So we can utilize such a synchronization source and calculate power.
Okay, thank you. And that carries over into ETAS, of course, because it's fully integrated with the PW.
Yeah, so we would, and Ike may also want to say something in this case, but generally the time synchronization that we get together for the ECU data would come from the power analyzer, and that's how we would time synchronize the ECU data together as well. So we would take the time synchronization from the measurement that we're getting from the power analyzer and synchronize it with the ECU data.
Yes, that's correct. Like the information is sent out over the integration platform here, and that's the advantage of the system as well. Like we're not using, like Inca is not measuring a voltage output from the power analyzer, or we are not doing an XCP gateway. We are getting the message with a proper digital integration that allows us to be able to get the timestamp from the device as it's configured in the device.
Thank you very much. Interesting times, interesting setup. Well,
oh, great. That was a great question, by the way. I appreciate that question. That was a really good one.
Yeah, thank you. With that, I want to thank you all for attending. Those are all the questions we have right now. If you have further questions, you know how to reach us. I want to thank you all for attending. I want to thank Kevin and Enrique for the presentation and demo, and the panelists now and Tim for answering all the questions, the easy ones and the hard ones. Again, if there are further questions, please contact us. We are here to help you. I want to thank the audience for spending almost an hour with us, and wish you a wonderful rest of the day. Thank you.
Thank you, everybody.
Thanks.